Okay, before the break we just started with the border balance estimation. We said that the input should equal the output, and we discussed a little bit when we can neglect the dsdt. Let's briefly look at the water balance, or the processes that make up the water balance in a real catchment. Well, a real catchment is a very rough simplification of reality, what you see here. The input to the system is the precipitation, rain or snow. Yeah? This rain or snow hits the surface. Some of it stays at the leaves or goes down in the soil surface. Then we have so-called infiltration. That's the flow of the water into the subsurface. Yeah? Or it does not infiltrate, so there's overland flow. Or from the infiltration it goes further down to the groundwater, then we talk about percolation. Or it goes laterally, so-called as interflow or rapid subsurface flow. Or when it's in the groundwater, there's some sort of groundwater recharge happening after the infiltration, percolation, and then the groundwater somehow flows to the river again. And then in the river, flows into the next river, to a lake, or into the sea. Let's look at this a little bit more in the equation mode. And I would like to explain that on the blackboard. Maybe make a bit more light for a moment. No. Yep. Maybe you want to follow that explanation now also with some. Oh, where is it? Here. Ah, yeah, that's maybe a good idea. So first I write down the water balance equation. Again, precipitation equals runoff plus evaporation plus ds dt. And when you wake up in the middle of the night, from now on, you always remember that equation. Yeah. Let's try to illustrate that on a hill slope. This is our hill slope. We have some vegetation here. This is a tree. There's some grass. I'm not the most talented painter. I do know that. Yeah. Maybe some roots here. Good. And then we have maybe a groundwater table like this. So this is the Earth's surface. This is groundwater. Hope you can read this. So what is happening now? Rainfall is falling. That's the input to the system. I call that the P, the precipitation. Some of that water is falling on the leaves. Yeah. So it's sitting here on the leaves. What is happening on the leaves? It's called interception, and from there it's evaporating again. We call that interception evaporation. Huh? So it goes back to the atmosphere. I call that EI. Evaporation from the interception storage. I need to get this a bit down. Doesn't want to go down anymore? Good, leave it there. That's the EI. Yeah? Other water hits directly here on the surface of the soil. What is happening from there? Some is going into the soil. That's the infiltration. Yes? Others maybe does not go into the soil. You all have seen heavy rain, and then there's overland flow. So that's a run of a lateral flow. I call that RS for a moment. Runoff surface. Yeah? Runoff at the surface. Also, some of the water evaporates directly from the surface again. If you've seen after rainfall, the street, everything was wet. Then the rain is gone and it dries up again. So there's evaporation from the soil zone. I call that ES. Could be the surface or the soil. You also have evaporation out of the river directly. Yeah, it's also a kind of a surface evaporation. ES. Clear? So what happens to the water? Well, the runoff goes then here to the river. Yeah, that's all this RS. So what happens to the water in the unsaturated zone, in the soil zone, after it's infiltrated? Yeah, but before we have capillary rise, some of the water goes down to the groundwater. Yeah? Wait a minute, you're too fast for me. Let's first, we have water here on the soil storage. Yeah? Therefore it's a soil storage change per time. So as soon as water is here stored here on the soil surface, it's a ds dt, but I call that SS for storage on the soil. If the water infiltrates into the soil zone, yeah, then we have here in this unsaturated zone a ds dt for, I call it U, SU for unsaturated zone. If it percolates down to the groundwater, we have a ds dt, and I call that SGW for groundwater. There's water goes down the ground surface to the groundwater table rises, then you have more storage in the groundwater. Yeah? You understand these three ds dt? One is on the surface, one is in the unsaturated zone, one is in the groundwater zone. Yeah? What happens to the water in the unsaturated zone? Some goes down to the groundwater, but others maybe also goes laterally, subsurface flow, or interflow it's also called. I call that R, maybe U, for unsaturated flow. Yeah? Some of this groundwater also flows to the river. I call that RGW for groundwater. Is that clear? So we have flow components. So far with the evaporation, we had evaporation from the surface, yeah, the ES. We had evaporation EI. I hope you can see that this is I, yeah, for interception evaporation. How else can water be evaporated? Transpiration. That's plants are taking up water and transpire the water. So plants have here their root channel in the soil zone, take up the water, it's transported through the tree, for instance, going to the leaves and leave the leaf back to the atmosphere. I call that E and a T for for transpiration. Yeah, it's a flux. You know, I also transpire while I'm standing here. I need to cool my body while I so much heat, so much talking. So then I transpire water, and therefore I keep my body temperature cool. And a bit a similar effect is plants. So we go that into very much in detail on Friday morning. But a similar thing is happening with plants as well. That's transpiration. Do I have everything? Maybe not now. So what we maybe some. So we have a couple of evaporation fluxes. The evaporation from the soil surface, evaporation from the interception storage, evaporation through transpiration, and evaporation from the river, which is also a kind of a surface evaporation. Yeah? We have different type of runoff components. I make them blue. We have the surface runoff, the RS, the unsaturated zone subsurface runoff, RU we call that, and we have the groundwater runoff, RGW. Yeah, these are three different groundwater components. Yeah? And then it all goes here through that river, and you have flowing into the river, and that's then the final runoff. I just make a big R. And we have different storage changes. I make the storage changes green. We have storage change in the... Oh, I've forgotten to write down. What happens if water falls on leaves? It's interception. Yeah. So there's a little bit of water stored on the leaves. Therefore it's ds dt, but I call it SI because it's water stored in the interception storage. So we have different storage changes. For instance, in the interception storage. Water change in the surface storage, change of water storage in the unsaturated zone or in the groundwater. Yeah, these are different type of storages. Is that clear? Therefore, we can write down this water balance equation a little bit more in a sophisticated way. So the precipitation equals the evaporation plus the runoff plus the SDT, same equation again. So precipitation equals the ES, yeah, the soil evaporation or surface evaporation, the evaporation from the interception storage, EI, plus the evaporation from the plants directly, that's the transpiration. Yeah, these are the three main evaporation fluxes. Plus runoff, we have runoff at the surface, RS, runoff on the in the unsaturated zone, RU, plus runoff in the GW, in the groundwater. Yeah. Plus we have a number of, oops, I do it this way, DSDT, make an I here. These are a number of storage changes per time step. Yeah, you see the equation, make it again. Green, we had the storage changes. Blue, we had the different runoff components. And orange, we have the different evaporation components. Yeah, and that's our water balance equation, a little bit more the way hydrologists like to apply them. Yeah. Is that clear so far? What is simplified? What did I forget? If you think about where water can be stored in a catchment, we said it's stored on the surface, on the canopy, on the leaves, yeah, the interception storage, or on the surface, or on the saturated zone, or in the unsaturated zone. Where else can water be stored? One after the other, what? The depression storage, we could argue that's part of the surface storage. That's a little bit of small depression on the surface. It's part of that. But if you sometimes it may be useful to have a separate DSTT for depressions, if the depressions are very important in your catchment. What else? Ground. In the ground. But we have unsaturated and saturated groundwater. In the soil moisture. Soil moisture for me is the DSU. The air moisture. Aha, it's above the catchment in the air. Very good. Yeah, you said the same. Okay, I forget about that because we solve the water balance not for the atmosphere. We only serve it as soon as it kind of is in the hitting the continental surface, you could say. Yeah. Okay, but it's true. What else? Where else can water be stored? Channel storage. So I didn't put a DSDT here in this one. It's true. I can enlarge and make it DSDT and SC for channel. Yeah, very good. What else? How about snow and ice? Also didn't put there, huh? Could be another DSDT. Yeah. Precipitation, for instance, solid precipitation, snow falling into a snowpack. Building up a snowpack is also a water storage in your catchment. Yeah. It's a DSDT. I write it up here maybe. DSDT for ice and snow. Yeah, I've forgotten about this. Where else can water be stored? Think about human systems. Water supply, pipes, sewage treatment plants. Yeah, all that in an urban area, water can be stored there. Yeah, clear. Where else? In the vegetation itself. Yeah. You know that a tomato is some 90% of water. So if the tomato grows, there's a lot of water stored in the tomato itself. Yeah. In all sorts of organic material, also in living material like humans or animals, you have some storage. Yeah, but little. Reservoirs and lakes I also didn't mention. Maybe I write one more down here. If you have here a reservoir, this should be a reservoir. I hope you can see this here. I do another DSTT and I call that a lake. Yeah. I think these are the main storages. Yeah. Something else I've forgotten? Yeah. Urban or human storages I also write down somewhere that you just don't forget. ds, dt, urban. Yeah. Good. So the water balance equation is clear from now, I hope. And never forget the SDT. That's the most interesting of hydrology. If we wouldn't have the SDT, it would be only half that interesting. Now, how do I move this down again? Hello? Yeah. I hope I do it in the break. Let me continue with my slides. Good. This is the same, just with the different parameters. What is capillary rise? Somebody said that. I've forgotten about it. Capillary rise is from the saturated zone via capillary forces to the unsaturated zone and maybe all the way up to the surface. That's capillary rise. Somebody said that. I've forgotten who it was. Something else I've forgotten? No. Roughly, I explained the water balance equation and we wrote down a couple of variables, how to call them. This is the same equation which I just showed now, and you see here you can also summarize the interception processes with the dSi dt plus EI. So that's the change in interception storage and interception evaporation. You can summarize surface water processes, root zone moisture process, soil moisture processes, and groundwater process. You can also summarize like this. And it's still the same water balance equation. Yeah? And this is the key, this is the fundamental basis of hydrology. Here you see again another slide explaining the different parameters. Look at that carefully and be able to use the right terminology. Yeah? Partly in science is communicating exactly about the right topic. Therefore it's very important that you use a common terminology. In all textbooks and also in the work of the Laat, the textbook you have in front of you, all these terms are properly defined. Yeah. This is the same more in a schematic diagram with boxes and in a flow chart. What you see here, two different colors. For yellow, for the fluxes, and blue, light blue, for storage. If I explained it here, we said like water can be stored in the unsaturated zone or flowing down to the groundwater. The flux is the movement of the water, like from the unsaturated zone to the groundwater, we call that flux percolation. Or from the soil surface into the unsaturated zone or into the soil, we call that, how do we call that? Infiltration. Yeah, that's the flux. The storage here is the unsaturated, the soil moisture storage, for instance. Yeah? So don't confuse fluxes and storage. The fluxes is connecting two storages. And they also have different units. We'll come to the units later. Is that clear so far? Homework here. I have a slide, and you indicate the storage volume. You think about inflow and outflow components for a simple reservoir. It's nothing else than just putting some words behind this equation, which you just wrote down. Do that for yourself at home. You don't need to show it to me, but I strongly recommend to do these simple problems which I have in between always in my slides. Yeah? And think about answers. You can do that in a small group with your neighbor or whatever. You don't have to hand in these exercises, but I recommend for you doing it. In general, we expect that only that is clear with a study load. For every lecture you get here, we have a study load multiplier times 2 or 3, depending on the lecture. That means if you have to listen to me 1 hour, we don't think that that's the hour. We think that 2 or 3 times the time is the total time expenditure. So probably 2 times that hour you have to study at home by reading books, by looking to my PowerPoint slides again, and so on. For exercises, we have a multiplier of 2. For design exercises, multiplier of 3. It's all in the headbook, all described there. So we expect that the time you're sitting here, we expect you to work at least another or even twice that time at home to really understand all that subject. Sometimes I also go very fast, but I'm teaching master's level, so I cannot go too slowly, and I think I try my best not to go too fast. If I'm really too fast, if I lose you, then you tell me. But on the other hand, we have to go through quite some material. But realize that twice the time you sit here in my class, we expect you to work at home at the same material. Yeah? And I think on average it adds up to a workload per week of 46 hours or something, including exam preparation. That includes exam preparation. Yeah? That's the warning. In a day like today, I think you have 8 hours of lectures, most of you. Huh? That's terrible. Of course, in the evening you're tired, I know, and you cannot just twice the time repeat this, because then there's no time to sleep anymore. I realize that. But there are other days that are less busy, huh? When you really have to go through the slides again and get it into your brain. Well, sometimes also hydrology introduction is some of you might know already from courses you took at undergraduate level. Yeah. For some it's only a refresher. They heard that all before. Yeah. Who heard the water balance equation before all this discussion we had so far? Yeah, some of you, half if I look at this. Yeah. So then it's just a refresher, and you don't need twice the time to really understand this. But for others it might be a bit new, and they need a bit more time. Yeah. But on average, the average student, we expect to work 46 hours on average. If you're smarter, or you have a better base education, you might do it in less time. If you need a bit more, in particular at the beginning, you have to work more. Yeah? That's some guidelines. Good. How do we break the hydrological year? I hope you can you read this? This is always a hydrological year. 1st of January, 1st of August indicated there. I know 1st of January, 1st of August is exactly not a half a year, but what you see here is the seasonal variability of the hydrological year. This is very common. Many of you also come from the tropics, where you have 1 or 2 rainy seasons per year. Yeah? So it's maybe not very wise to break the hydrological year on the 1st of January. So you don't want to break the hydrological year in the middle of the rainy season, because then it really depends on how the rainy season is this year, coming early or later, when the peak is, before or after. It's always better to break the hydrological year in the dry season. Therefore, where is my pointer? Therefore, you don't want to break the year here, but rather in the dry season here, for instance. Yeah? In the humid temperate climate here in Europe, we usually have starting of the hydrological year at the 1st of November. Because after the summer, and summer low flow period also in many of our catchments, before the winter comes again, we start the year fresh. The winter is not so good to start the hydrological year 1st of January, because we have snow. That means some precipitation falling in November, December, sits as snow in your catchment in the mountains and is not discharging till next year. So there's a DSDT transferred from one calendar year to the next calendar year. And then it's more difficult to solve the water balance equation. Therefore, it's much better if you break the hydrological years in our climate here in the Netherlands at the 1st of November and the 31st of December. In alpine climates in Switzerland and Austria, they have the hydrological year at the 1st of October, because their snow starts already in October, not only in November. Yeah? These are some conventions. If you are from Tanzania, and you have in most places of Tanzania, for instance, 2 rainy seasons, Masika and Wuli, I think they are called locally there, and I think one is November, December, January, and one is March till May or something. Yeah? And then it's maybe wise after these rainy seasons to start the new hydrological year. Yeah? So there are different conventions in different countries, but it's not always wise to follow the calendar year. That's maybe the main purpose. Is that clear? Good. Next point I want to introduce is the so-called runoff coefficient. Here you have a water balance, a very simple water balance from a town in the north of the country, in Lelystad. You have here it's millimeters per year. Sorry, the wrong unit here. Millimeters per year. Yeah. It's the annual rainfall is 867. We take that 100%. The total evaporation is some 316. That means 46% of the total rainfall are evaporating, and 54% of the total rainfall are discharging. Discharge in this city is sewer discharge and subsurface drainage. Yeah, there's no real rivers or so in that catchment. It's a artificial town that was put there artificially with reclaiming land. Yeah, but you see here the so-called runoff coefficient is 54%. Yeah, what is the runoff coefficient in your hometown? What do you think? Who wants to say? Do we have somebody from the tropics, from Malaysia or Indonesia? We must have somebody, huh? Nobody. No, nobody. Okay. From any other part of the world. Do you know your annual rainfall in your hometown? Who wants to say? It's not an exam, don't worry. 1,200. Where are you from, if I may ask? Trinidad, from Greenland. Yeah, let's say 1,400 or so. And what do you think is the runoff of this? It's very hot there. There's a lot of evaporation. Huh?
Runoff is it should be very high.
Yeah, more or less than 50%. Okay, let's see. I think less. I've never been in Trinidad, but I think maybe 40% is runoff and 60% is evaporation, I would think. But we come to evaporation maps later now on Friday, so maybe we can look at it again. Yeah. Yes?
The runoff coefficient has to do with the soil surface, right? It's not stable.
Has to do with all the hydrological parameters that influence runoff generation. All these, you know, the final runoff is this R. And everything that happens before defines how much this R is. Yeah? The runoff coefficient is this R here divided by the P, by the precipitation. And all these processes here which we discussed, they all define the runoff coefficient. Therefore, what the surface is, what vegetation you have, what kind of soil structure you have, what kind of infiltration conditions, what percolation conditions, all this defines the runoff. Yeah. Yes, please.
In case of the flash floods, if the flash floods are coming, so all the rainfall is converted to runoff, so the coefficient will be maybe around 90 or 80.
Yeah. On short time scales, for small localized areas, if you have flash floods, it can be almost 100%, yes. Or if you have hard rainfall on a big sealed areas, impervious areas like a big parking lot, then there's almost no loss. Then it's close to 100%, yes. Yeah. But on long-term average, for larger areas, no, because a lot of water is then also infiltrating. This discharge is lost again. You know, all the groundwater recharge in Namibia, for instance, is not all, but a significant part of that arid country is also a lot of high runoff coefficient locally, but then the discharge is flowing in the river and then going back to the groundwater. Huh? It's infiltration of river water into the groundwater. It's very common in arid areas. So for the whole of Namibia, you have much lower runoff coefficient. Yeah.
So runoff coefficients, it means that it has to be divided, the area has to be divided, and then we have to make a cumulative runoff coefficients, because sometimes the hilly areas it is so much high runoff, but in some of the plain area the runoff is less. So it's like averaging.
Yeah, it's a long-term, the way we put it here is a long-term annual average. Yeah, but you can also calculate it for an event. We come to that next week. For an event scale, we come to that. Yeah. Okay. Here you see some water balance parameters for different catchments in the world. Let's look at the Nile. Yeah, in northern eastern Africa. Total catchment area is this. And then the numbers here are given in millimeters per year. Why do we give rainfall in millimeters per year? I said we measure a volume. Why do I give the number here in millimeters per year? Here's a volume, cubic meters per year. Should be per year actually here. But why is that millimeters per year? That's funny. Who wants to explain that?
Because it was measured in the rain gauges.
Exactly. What do we measure in the rain gauge? A water volume in liters or cubic centimeters. Yeah. But how is that then transferred to millimeters? Divided by the area. If we have a 1 square meter, a meter by a meter, and you have a water height of 1 millimeter, this is exactly 1 liter. So 1 liter per square meter equals 1 millimeter of rainfall. Yeah? We divide by the area. It's very important. Therefore, we give the water balance parameters usually in millimeters per time step, millimeters per year. And 1 square meter is 1 liter per, 1 millimeter is 1 liter per square meter. Yeah? Therefore, we give that in millimeters per year or millimeters per day or whatever. Yeah? This is cubic meters per year. This is wrong, should say per year. I forgot where I copied this from. I think it's on the book of Laat. I'm sorry for this. I need to be corrected. Yeah? Good. So the total rainfall is 220. Of course, now the Ethiopians say, oh, but in the Abai we have, how much rainfall do you have in the upper parts of Ethiopia, in the Ethiopian highlands? 2000 is high, but 1500 for sure you have in some areas. Yeah, it's very high. Yeah, but then you have other places like Egypt, Sudan. They have less than, some places less than 100 millimeters of rainfall. Yeah, and this is an average for the whole of the Nile. So that's average 220. Evaporation is 190. 30 millimeters is runoff. So the runoff coefficient is only 14% in the Nile. Yeah, so it is very dry, and then 86% already evaporate. There's not many water resources there in the Nile. Look at the humotropical, maybe the Mekong here. The catchment size, the rainfall in the Mekong is some 1500 millimeters on average. Yeah, on average. You have some areas above 2000 in Laos and Cambodia. Total evaporation is 1000. Therefore, we have some 500 millimeters. Why? Oh, maybe I'm lost here in the number. Wait a minute. Why is this not 500? 1500 millimeters of rainfall, 1000 millimeters of evaporation should add up to 500 millimeters of runoff. Why is it not? I'm confused now. Should add up. I don't understand, because the long-term average the SDT should be 0. So I checked the Mekong number. Sorry, maybe other catchments, let's double check if there's no Lena, 300 millimeters of rainfall, 140 evaporation, 212, yeah, 0.2 is the runoff. Yeah, there it fits again. So I'm not sure about the Mekong data. We have to ask Dr. Delac this week where all these numbers come in. But it should add up, of course. The input equals the output. Oops. Globally, if you have 100% precipitation, then about 65% evaporates through transpiration, mainly through forest, grassland, wetlands, crops, yeah, and about 35% are discharge. Some from the discharge is used for irrigation, for instance, yeah, so it's taking out, some of the water evaporates again. Some of us is also return flow, so going back to the river, and then discharge. That's then the return flow from irrigation. Yeah. But most of it is so-called green water. So this is water leaving the catchment via transpiration. But the blue water is the discharge. I bring in this terminology of green and blue water. Not that I like it so much. I even think some of the definitions are not very good. But it's very common to use. There's a lot of international talk nowadays about from green to blue. That means, from blue to green, that means using more water for plant growth. So using more waters from the rivers and the groundwater, mainly from the rivers, to use that for producing biomass, to use it for the fields, for irrigation, for instance. That's from blue to green. Blue water is a water resource in the river or in the groundwater. Green water is the resource when it is going through the plants, basically, for biomass production. Biomass production means food production. Therefore, in particular, in arid countries, there are programs from blue to green where they want to stimulate the efficient use of water resources for plant production. Now look at this so-called rainbow of water. Atmospheric water, sometimes called yellow water, but not so common. Most common is that the water from the transpiration, which produces biomass, is the so-called green water. Sometimes some authors, also Savenige, from whom I took this figure, he talks about the white water. White water is the interception evaporation here. That's this here. White water. That's the water sitting on the leaves and evaporating again. He also adds to it the so-called surface evaporation, what we call ES here, this here, because this water is all not productive. It falls on the surface, evaporates again, doesn't do anything for biomass production. Yeah? More important is the evaporation flux of the transpiration, the green water flux, and then the blue water flux are here. Therefore, I used also blue for the 3 different runoff components, and the water managers call a water resource blue water when it's water in the river. Some authors then also distinguish between blue water in water bodies like rivers and lakes, or deep blue water, that's the renewable groundwater. Some of the resources are also in the subsurface, and they also perform a groundwater flux. Call it light blue and deep blue. Yeah? But blue water is the flowing out water resource, you could say, while the green water is the uptake through the vegetation and biomass production. Is that clear? Difference between green and blue? Everybody understand the white water? The interception water. Okay. Skip this. Then is another terminology which I would like you to agree on, is the difference between runoff production or runoff generation and runoff routing. Yeah? Runoff production is the generation of rainfall of runoff through rainfall. So rainfall is generating a certain runoff. It's also called the effective rainfall. Which part of the rainfall does not generate runoff? The evaporation fluxes, huh? All the interception evaporation, soil evaporation, surface evaporation does not produce any runoff. Only part of the rainfall is producing runoff, the so-called effective rainfall. Also heavily used for hydraulic engineering design exercise, also effective rainfall. That's the runoff generation term. While the runoff routing, that's then as soon as the runoff is generated, for instance, you generate here overland flow, but this water still has to flow to this river, and from the river to the gauging station or to your city or to your irrigation scheme. Huh? And this spatial concentration of runoff, that's what we call runoff routing. Huh? This flowing together of generated runoff. Huh? That's the temporal distribution and concentration of the effective rainfall. So flowing on the surface or flowing in the rivers and then going to your catchment outlet or to your urban area or wherever you want to measure it. Clear? Difference between runoff generation or runoff production and runoff routing. Okay, good. Very good. You're laughing. Am I too quick with praising you? Okay, now we move on to understanding the catchment as a functional unit. Yeah. Before we looked already on the table with the water balance. Well, I didn't understand the Mekong number, to be honest. I don't know. I think there's a typo in that. But we did that for a catchment or for a river basin. The Nile and the Mekong we call not a catchment. Usually we call river basin because they're big things, or watershed. I think the North Americans always like watershed as a term. Yeah. I think the British English is more catchment, and basin usually is a bigger thing. But it's all the same definition. The catchment is the unit where we can do the quantification, where the input is the precipitation, the output is the runoff and the evaporation. This has some German, but I think you can understand this. This is the drainage network, and you have this is the catchment boundary. Here you have another example of a catchment from a work where we did some research in Austria. This is then elevation color-coded. Here it's up to 2,000 something meters. The outlet is some 1,000 something meters. And you see the different topography, different zones of topography. And you also see where we had some rain gauges, etc. But this surface area here, surrounded by the catchment boundary, that's the catchment. Very trivial, huh? Here you see some other examples from New Zealand. Here people were studying what is the impact of deforestation. So if you cut the trees, what happens to the water balance? Yeah? And to study that properly, they did completely clear cutting some of these small catchments here. Huh? The good thing is you see the catchment boundary very well. Yeah? But you don't want to suggest that to an environmentalist in Europe. We cut all forests and then we study what the impact is. But these were kind of nice examples, study areas where they studied the clear cuts. And still, the forestry practice in many countries is doing clear cuts in many parts of the world. Yeah. Ecologically, maybe not the nicest thing, but economically quite efficient. But you see here the nice catchment boundaries. Yeah? Here's an example from the Alps again. This is the river. This is a kind of a flash flood system in a very steep alpine environment. You see it's really very steep, you hardly can walk there. This is the outlet, and the catchment goes very close to this river, then maybe up here and down again. The very long shaped catchment. Here's already the next catchment, etc. Yeah. Sometimes the surface catchment does not agree with the subsurface catchment. This is what we try to explain with this figure. I hope you can see that. This is the catchment, very simplified, and the topographic divide is the blue line. Yeah? From here into these rivers here and up to this mountain. Yeah? From A to B, you see this profile. This is the topographic divide, topographic boundary. Sometimes the groundwater table, this is the shaded area here, there the groundwater highest level also has the highest level with the topography. That's this case. Here the topographic and the phreatic or the groundwater divide are the same. In other mountains it can well be that the groundwater, highest elevation of the groundwater table is somewhere else. So there's a difference between the topographic divide and the phreatic divide. Yeah? That means you have overland flow. When rainfall falling here, overland flow goes into this river. Yeah? Rainfall falling here, overland flow goes actually in this river. However, if it infiltrates to the subsurface into the groundwater, it still flows in this river. You see, depending on if you have overland flow or subsurface flow, the catchment is a different one. You also see this, two more slides and we break for coffee again. This is the river, the Danube, in southwest of Germany, the area where I'm originally from. This is quite a significant river. Yeah? Here's overland flow, you all believe me, and I was standing here taking that picture, and the whole river is infiltrating to the subsurface. And it disappears. Really, I was standing here and the whole river disappears. And people were long thinking, so where is that water going to? And they did so-called tracer experiments with oil and salt and isotopes and whatever. And then they found 11.7 kilometers away, quite a big spring with discharge of up to 5 cubic meters per second. Yeah? So very, very big spring. So all that river disappearing here comes at a spring out somewhere else. For the geologists, this is limestone aquifers where you can have sometimes very funny water divides. This is the Danube, this is the Rhine, maybe for the people know in geography a little bit, this southwest of Germany. This is the Danube River. And then you have here an area in Germany where you hardly have any overland flow, hardly any rivers. Do you know about this in your home countries as well, maybe? Yeah? Maybe there are also some limestone areas where hardly any overland flow is generated. All overland flow goes to the subsurface, yeah? Or almost all. And this is also happening here. Here the Danube comes along, flow here, but here it looks like if it was always be flowing this direction to the Black Sea. Not true. Sometimes the whole river on this stage here disappears and discharges in this area. Yeah? To get your geography right, this is the Danube. So the Danube goes into which sea? Into the Black Sea. Right. It starts here in Germany and then it flows here to the east, going to Austria, Hungary, Romania to the Black Sea. This is the river Nile. The river Rhine. The river Rhine, and you will all visit that river. You can see it here in Rotterdam already, parts of it, and you will visit that during the future. This is coming from Switzerland, a little bit of Austria, very little bit of Italy as well, actually, and then goes to the Lake of Constance. This is my hometown, but that doesn't matter. And then goes here the river Rhine to Holland and to Rotterdam. Yeah, going to the North Sea. So depending if the Danube if it's flowing during high flow season, then the river is generated here, flowing to the Black Sea. But sometimes the whole river disappears, infiltrates, and goes to the river Rhine and to the North Sea. Yeah? So you see, in Europe it's really depending on the water level of the Danube, Is the water going to the Black Sea, to the Balkan, and to the Black Sea, or to the North Sea, to the Netherlands? Yeah. You see how catchment boundaries are linked to each other. Is that clear to everybody? Can you understand how difficult it is to make a proper water balance equation for this? Yeah? Because the rainfall you can estimate. Let's assume you have enough rainfall stations, then you can estimate that rainfall. But then you don't know how much water actually goes into the subsurface and goes out in another catchment. Yeah? And that's the challenge in hydrology, to get these boundaries right. Is that clear?
So the basin is below the full basin.
These are big river basins. The Danube is the largest in Europe, and the Rhine is the second largest also in Europe. Yeah.
So in one basin we have the two rivers.
Yeah, you have an area where it depends. Water can flow to the Black Sea or to the North Sea. This is a complete different geography in Europe. That's the east or the west. And in the former times, people did all sorts of funny things. You know, they tried to avoid that the water is infiltrating here, and they put in textile and so on, tried that the water is not disappearing. And these are also two different administrative units, and there were a bit of bit of war even between Schwaben and Baden in Germany. It's quite a funny history. They try to avoid that, but it's impossible. Water finds its way. You would need a lot of concrete to avoid this, and they didn't have them. Here you see that again. That's the Donau in German, the Danube flowing here. Then water sometimes completely disappears, going into that spring and flowing then here to the River Rhine. You also have these challenges. This is a picture from the Amazon near Manaus, and then you have also the same with but it's similar, not the same, sorry, it's similar thing with the Orinoco. I think it also depends on the water level of in the river, if it flows the one or other direction. Do we have somebody from that region? Can explain that to us? Northern Brazil? No, we don't have. But it's really depending on the water level, if it flows that direction or into the other river. Do you see how sensitive that is? And in particular in lowlands, when the topography is flat, the water level and the groundwater level can really define it flows that or that direction. The worst is in the Netherlands. If you're on a bike and go around Delft and so, these are all artificial channels. These are all man-made and controlled. There's no natural river here, huh? And they're all depending on pumping. And depending on how much water you pump on the one or other direction, the water flows in this or that canal. It's all artificial hydrology, so it's not exciting for us. Yeah, it's all pumping hydrology. It's a bit boring, huh? But you see the challenge. Often there's no clear divide, or there are even temporal variable boundaries. And you need to know this if you want to make a water balance. Yeah, you need to know. Also, in parts of the Netherlands, I just explained, you have a lot of import and export of water. Okay, let's break for coffee.